Welcome to part 3 of Introduction to Thermodynamics. This lecture is going to be the basis for rest of the course. Part 1, part 2 has given some fundamentals. Now with this part 3, you will have a sum up of all the fundamentals related to the course. Now let us see the different types of energy. First is internal energy, and then we will see work. So, internal energy. Internal energy refers to the energy contained within the system. I am bubbling with energy to do this job. It's my capability. This is internal energy. So, it refers to the energy contained within the system. The energy represents the overall energy of the system and may include many forms of energy such as potential energy, kinetic energy, etc. So, it also includes exothermic and endothermic. In chemical reaction, we know about the energy transformations, and basic thermodynamics provides us the information regarding the energy change associated with the particles of the system. So, internal energy is the energy wherein which it is contained within the system. So, for example, you have a cylinder, you have a piston. So, this is the surrounding outside. So, you apply heat. When you apply heat, the system, ideal gas, whatever is there, it starts expanding. The energy gets into it, starts expanding. Moment it is started expanding, you can see the piston is moving in the upward direction. So, now here if you see surrounding, then you have a glass jar, then ideal gas is filled. So, here the internal energy is U1. So, when you heat it, it becomes final internal energy U2. So, W is the work done which is trying to push the piston up. So, what is the work done? Okay. So, the difference, the final minus initial is nothing but is the difference in internal energy, which is nothing but Q minus work done. So, the work done is W. So, when you try to heat it, the molecules move randomly in the direction has internal energy. So, it moves left and right, up and down, and then slowly the piston is pushed upward. So, internal energy is the amount of energy contained within the system. The energy represents the overall energy of the system, which includes potential energy, kinetic energy. It is the total energy within the system, that is internal energy. It is the sum of many types of energies like vibrational energy, translational energy. Okay. So, all these things get into internal energy. It is very important. Internal energy, what is the energy is there within the system such that the job can be done. For example, you are trying to think of an IC engine. In IC engine, what happens? You have a cylinder, petrol engine, you have a cylinder. Now, you compress and push the air mixture inside. You have a spark plug. This spark plug ignites. So, there is a explosion. So, there is a heat which is getting generated. Moment there is a heat getting generated, the piston goes up. Moment the piston goes up, this is connected with some link, and that link in turn is connected to in the engine, and now the vehicle propagates. Okay. So, that is what we are trying to talk in this. Right. So, that is Q minus W. So, it is an extensive property and a state function. It is the change in internal energy accompanying a chemical or a physical process that is of interest, and this is a measurable quantity. Its absolute value cannot be determined, but experimental change in internal energy change can be determined as this. So, its absolute value cannot be determined. Please underline, its absolute value cannot be determined, but experimentally change in internal energy can be determined by this equation. Is that clear? Absolute value cannot be determined, but experimentally you can get it done. So, the sign conversion for the internal energy, exothermic, endothermic. Exothermic is once the reaction happens, it ejects out heat, that is exothermic, it ejects heat out. When you say endothermic, it absorbs heat. Okay. So, if it is exothermic, we always say delta U. Delta U is nothing but final energy in I energy minus the initial IE minus this is what is delta U. So, if delta U is negative, then it is called as exothermic. If delta U is positive, then it is called as endothermic. For example, when you try to have the toffees and then after having this toffee, when you suck air, you feel the coolness in your mouth. So, that is nothing but endothermic reaction. The internal energy U or E, it is directly depending on temperature, pressure, volume and quantity of matter. So, if the temperature is high, U changes. If the pressure which is applied is high, E changes, volume changes, then quantity of matter also changes the internal energy. The factors which are affecting the internal energy is the heat passes in and out of the system, tries to change. The work is done on or by the system, or a matter enters or leaves the system is a factor which affects the internal energy. So, friends, I have introduced path function. First, I introduced state function. Then, I talked about path function. Then, in path function, it is very clear. Initial final state alone, it does not depend, but also it depends on the path of the process which is followed. Then, we got into the thermodynamic energies. The first energy what we saw was internal energy. Internal energy is the capability of a system to do something, right. It refers to the energy contained within the system. So, here you can have potential energy, kinetic energy, vibration energy, translation energy, many things, right. So, when we try to talk about these energies, we also try to talk about how do you measure these energies. So, this is what is given in the statement. Its absolute value cannot be determined, but experimentally change in internal energy A can be determined by A into U is equal to U2 minus U1. So, it is basically U is nothing but U2 minus U1 by A. So, you can try to figure out what is it, right. Then I introduced exothermic and endothermic. Exothermic is heat is getting rejected. So, it has a value negative which is absorbed, which is positive. And the last point is how does this internal energy change, which is quite natural, right. When the rod is heated, it radiates, right. When the pan is heated, it radiates, right. When the pan is heated and you put milk, there is a chemical reaction. So, heat passes into or out of the system, then work done in or out of the system. So, now the next energy is work. Work done by the system is defined as the quantity of energy exchanged between a system and its surrounding. If I throw heat outside, so it is work done. When I throw cold air inside, work done. Work done by a system is defined as the quantity of energy exchanged between a system and its surrounding. If you want to have, this is a glass tumbler where you fill with cold water. Now, when the exchange happens between the system and the surrounding is nothing but the work, right. The work is completely governed by external factors. Suppose if I put it inside a refrigerator and keep this glass, what will happen? So, the performance changes. So, that is what I said. The work is completely governed by the external factors such as external force, pressure or volume, change in temperature, etc. So, work done is nothing but the quantity of energy exchange between the system and its surrounding is work done. So, if you look into it, work done, the units are always joules, and then if it is joules per second, then it becomes watt. So, the energy whatever you apply to your house, when you put an energy meter and then draw electricity into your house, we always look at what is the work which is done there, right. The work done is nothing but the amount of energy transferred, which is nothing but force into distance. distance moved in the direction of the force. So, W is nothing but delta E. What is E? E is the internal energy. So, W can be defined as force into distance moved in the direction of the force, W into Fd. The unit for force, the unit for work is always joules. So, delta E, energy transferred, is also in joules. The force is in newtons, D is in distance, which can be in meters or millimeters or microns. It is a linear scale. So, through this, what are you able to do is, you can try to figure out how do you calculate work done, right. Work done is equal to delta E. Work is a mode of energy transfer to or from a system with reference to the surrounding. This is always compared to the surrounding. If an object is displaced through a distance d against a force of magnitude F, then the amount of work done will be written as W equal to F into D. The work associated with the change in volume. Change in volume, if you go back to the piston example, you will see V1, V2, change in volume, delta V. The work associated with the change in volume of a system against the external pressure is called as mechanical work. Suppose if there is a piston, there is a dead weight of the piston. Now you heat it, the volume expands. So now delta V is the change in the volume of the system against the external pressure. What is the pressure here? Here it is nothing but the load, right, piston load. So that is mechanical work. So mechanical work can be defined as P exit brackets V2 minus V1, right, final volume minus initial volume, which is nothing but delta V, P exit into delta V. So P exit is the external pressure, delta V is the increase or decrease in the volume. You can have vice versa. If you have a cylinder and then you have a piston which is very heavy in load, so what happens, even though you try to expand, this piston's weight will be very high, it will try to slip down. So what happens, the final volume delta V, it can be positive, that means to say it can be V1 minus V2 or it can be V2 minus V1. So you can try to have the positive value or negative value. So that depends on delta V. Okay. So the increase or decrease in the volume is possible. The work is a path dependent function. For example, when you apply very heavy load, right, let us take sponge inside a glass and have a piston. Now you try to press it from the top, the volume is reduced. So I am trying to give you an example such that you will appreciate volume can increase, volume can reduce. So it basically depends upon the energy what is there inside. The work is a path dependent function. Work done on a system increases the energy of the system and work done by the system decreases the energy of a system. Note it down, this is a very, very important term. Work done on the system, work done on the system increases the energy of the system. The work done by the system is a decrease the energy of a system. So you friends, you can sit down and try to make at least three examples for both these things. So that can be a home assignment for you, so that you go back and refer or think even. The work done on the system increases the energy, compressing. The work done by the system decreases the energy of the system. So decrease the energy means expansion, whatever you are doing. Okay. So let us see the thermodynamic works. So one is work, generalized to force, effect and expression. So this will try to give you a formula based understanding. Displacement work, right, which is the generalized force is difference in pressure. Effect is where there is a change in volume, that is dV. So the expression is going to be delta W is equal to P into delta V. When we talk about mechanical work, it is difference in force. So here the change in position will be there dl. So mechanical work will be dW, d means delta W is nothing but force multiplied by dl. The surface energy work is nothing but surface tension. So change in the surface area is dA. So the work done will be delta W is equal to surface tension into area change. For example, you try to take a cup and you keep it at the open atmosphere, you keep it. Now what you do is, you take the same tumbler or the glass or a paper cup, you just immerse 20 feet down into water. You see what is the amount of pressure it is exerted on the surface. Now it shrinks. Now you go 100 meters down, it becomes a very small cup, right. So that is nothing but surface energy work. So surface tension is sigma. So sigma into dA. Now electrical work is nothing but the potential difference voltage V, which is change in the amount of charge dq. So it is nothing but dW is equal to potential difference. Potential difference is nothing but voltage V2 minus V1, higher voltage minus lower voltage, that is delta V. So that is V into dQ. So if you look at it, these are the expressions and these are the work done which is there in the consideration, which we have discussed till now. Okay. So in the thermodynamics work done, there are two conventions which we have to follow. The first convention is going to be work done by the system, W will be positive, when the work done on the system will be negative, right. The mechanical work has two energies, one is kinetic energy, the other one is potential energy, kinetic and potential. So potential energy is mgh. If you want to look in from the design perspective, it is nothing but half mv square. So the thermodynamic work, right, the thermodynamic work is thermodynamic work and heat put together hits the internal energy. Thermodynamic work, what we are seeing here, thermodynamic work, heat put together gets into the internal energy of a system. So the third work, thermodynamic work, the first thermodynamic work what we saw was internal energy, we saw internal energy, then we saw what is work, then work we had seen the formulas. Now we are going to see the third one is nothing but heat. What is heat? Heat in the thermodynamics is defined as a kinetic energy of the molecules of a substance. Heat in thermodynamics is defined as the Ke, kinetic energy of the substance. Heat and thermodynamics together forms the basis which help processes designer and engineer to optimize their process and harness the energy associated with the system and surrounding. Very, very important term. Heat and thermodynamics. We have studied what is thermodynamics. Heat and thermodynamics together. Thermodynamics work and heat together, right, forms the basis which helps to process designer and engineer to optimize their processes and harness the energy. The heat energy flow always flows from a higher temperature to a lower temperature. The change in internal energy delta U is nothing but Q minus W. Q is heat added to the system, W is work done by the system. Q minus W. The change in the internal energy of a system is equal to the heat added to the system minus the work done by the system. So we have already understood what is work, what is heat you have understood. So internal energy change is given by this. So heat is the third thermodynamic work. So internal energy is a state function. Change in internal energy by doing work. We take a system containing some quantity of water in a thermos flask or in an insulated beaker. The manner in which the state of such a system may be changed will be called adiabatic process. You will see what is adiabatic process in the course of time. We take a system containing some quantity of water, pour this water into a thermo flask, right. The manner in which the state of such a system may be changed will be called adiabatic process. Let us call the initial state of the system as state 1 and its temperature T1. Let the internal energy of the system be state 1, be the energy U1. We can change the state of the system by two methods. The first method is going to be by doing some mechanical work, say 1 kilojoule, by rotating a set of small paddles and thereby churning water. So what we are trying to say, you see here. So we are trying to understand the adiabatic, right. The manner in which the state of such a system may be changed will be called as adiabatic process. So now what we are trying to do is we are trying to make two different methods, the change of the state of the system. The first method is you take a beaker of water and then what you do is you put a fan there, a stirrer there, and then you rotate, right, by rotating a set of small paddle, thereby churning the water. You don't, the water temperature, whatever it is, you are churning it. For example, you try to take morning milk, in that you put a Bournvita and then use a stirrer, you keep stirring it, right. Let the new state be called as 2 state and its temperature be called as T2. It was found T2 is greater than T1 and the change in temperature is delta T is T2 minus T1. Let the internal energy of the system in state 2 be called as U2 and the change in the internal energy will be called as delta U is nothing but U2 minus U1. This is one way. The second method is we now do an equal amount of electrical work with the immersion of a immersion rod and note the temperature change. So, you try to push an immersion rod and then you try to heat the immersion rod. So, now the temperature of the water goes higher. So, we find that the change in the temperature is the same as the earlier case, T2 minus T1. The internal energy whose value is characteristics of the state of a system, whereby the adiabatic work was required to bring about the change in the state is equal to the difference in the value of U in one state to the another. So, we are now trying to explain the adiabatic work. When the internal energy, so two things, right? One is you put a temperature, you stir it. Why are we insulating it? So that the heat does not go out. You just stir it. So, that is what mechanical is done and that is what thermal is done. So, the internal energy U whose value is characteristics of the state of a system, thereby the adiabatic work was required to bring about a change of state in equal to the difference between U in one state and in another state. So, delta U is given by U2 minus U1. Therefore, internal energy U of a system is a state function. Now, what are we trying to do? We are time and again trying to say that internal energy and state function. If you go back and see where did we discuss all these state functions. So, this is a state function we defined. State variables or thermodynamic parameters depend only upon the initial and the final state of the system, right. So, the change in internal energy by transfer of heat. When we try to keep a vessel and when we try to heat it with a burner, there are three types of heat transfer can happen, which is radiation, convection and conduction. So, that is why if you see all the pans which you are using in kitchen, they will always have a poor conductor handle, which will be made out of polymer, bakelite or ceramic, some material like that. So, if you have the same material of pan as well as the handle, then when you try to heat the pan, the handle also gets heated. So, sometimes people make a wrong choice of material selection by just looking at the aesthetics, but you have to choose a non-insulating material when you are trying to do a heat one. So, convection and radiation. So, we will see all the three in detail. Change in internal energy by transfer of heat. The energy that flows across the boundary of a system, the energy which flows across the boundary of the system during a change in its state of difference in temperature between the system and the surrounding and flow from higher temperature to lower temperature is called as a change in internal energy by heat transfer. When you bring about the same change in the temperature by transfer of heat through thermal conduction walls, which allows the heat to pass through it in and out of the wall. So, that is conduction. Let us take a water at a temperature T1 in a container made out of copper as it forms thermal conduction walls. So, this is thermal conduction walls. If you want to replace it, you can also put glass. So, there will be no conduction. So, you can put an ice here and then ice cream you can put and then put a wall here which is of glass. So, there will be no conduction, right. But here we want heat to go inside. So, we put a container of copper, right. So, enclose it in a huge heat reservoir at a temperature T2. The heat absorbed by the system water is Q can be measured as T2 minus T1. In this case, the change in the internal energy delta Q is equal to U, where no work is done at constant volume. Keep that in mind, no work is done in constant volume. before getting into, I have explained about conduction. I will also explain about radiation. Anything which rejects out of this boundary from heat, that is radiation. Conduction through a solid and heat from here goes there. What is convection? Convection is nothing but when I start heating it, there is, what happens is the hot water, whatever is there, they slowly start heating up and then they become slightly lighter. They keep going up. So, then the cold water, because it is a closed volume, so the cold water, whatever is there, is getting pushed down to the empty space. I am giving you an analogy, but there is not an empty space. So, here what will happen? The hot water will become lighter and it will go up, and that in turn wherever it moves up, then the cold water will come. Now, you see there is a swirling action. There is a swirling action. By doing so, what will happen is the water which is hot at the bottom will try to slowly transfer the energy. So, then at the top also you will try to have the heat. So, this process of rotation and movement is nothing but convection. So, friends, in this particular chapter we had a fundamental understanding, and it is a fundamental chapter. So, here first we saw what is thermodynamics, and then we saw laws of thermodynamics 0, 1, 2, 3. Then we saw the state and explanation of 0th law, first, second, third law we saw. Then there was a classification we saw is microscopic and macroscopic approach, we saw that. Then the kinetic molecular theory of gaseous state, we saw that. Then assumption and postulate. Then features of pressure of a gas we saw. Then kinetic interpretation of temperature of a gas. Then 3 different systems: open loop system, closed loop system, isolated system. Then intensive, extensive thermodynamic properties. Then we saw about the state, path functions. Then we saw about the thermodynamic energy, internal energy, work and heat. And finally, we saw how can we say the internal energy is a state function. We saw the derivation. Right? So, in this particular chapter, we have used all these books for references to make this chapter. Now, before I close, I would like to give you some small assignments for you. Try to look at AC in your house and then try to make the state function, path function and process for this example. Take another example of you try to do kulfi or ice cream, I will say, right, the stick ice, right. So, in stick ice what happens? They try to maintain. So, what generally they do is they will have a bigger container, put ice in this container, put lot of ice in this container, then they will have a cold mold here, which is insulating mold. They pour whatever is the liquid here and then they place a stick. And then what do? They is they keep rotating this fellow, so that the entire the liquid gets solidified and then you get. For an ice cream which is generated like this, what is the state function, path and process? What is the final delta E which is there? Next, let us take an example of a pan. Okay. Inside a pan it is filled with water. Then in that pan I am trying to keep one more container, and in this container I am trying to boil an egg. So, this is another container. This container is filled with again water, right, and here is the container closed. It is floating or it is kept on top of water in the another container, and then I heat the system, heat. So, it is this is a conducting body, this is also a conducting body. So, now I heat from the bottom. Now, try to find out what is the state function, path and process along with delta E, and try to keep a very realistic temperature. For example, at what temperature water gets frozen, you know the temperature. So, ice also is there. So, try to be more realistic. If you are able to solve these 3 problems or and put your concepts very clear, then it makes this course more easy to pick up speed in the coming lectures. So, with that few words, thank you very much. We will continue in the next lecture more details about thermodynamic laws. Thank you.